Hi guys, this is Lily with Arc Network Security. I'm going to show you some stack smashing today. So we're just going to go and smashing the stacks. So first thing we're going to do is create the vulnerable program. We're just going to call it vuln.c, and we're going to include some of our standard headers here. And we're going to initiate our main function of our vulnerable program, argc char argv and curly brace. And what we're going to do is we're going to go char. We're going to create a buffer of 256, which is quite standard. And then we're going to do a string copy strcpy of our first argument into buffer. And then we're going to print that buffer as a string. Don't forget our new line, and then buffer. And then exit the program. So what we're going to do now is compile this. So gcc and we're going to disable some protections here just to make it easier for us to sort of play around. So now we have the program vuln. So if we say hello, it just basically returns what you give it. Well, if it's in one argument, right? So we're going to try and crash this. Before we do that, you should turn on your core dumps. So you limit so yeah, you limit xc unlimited. My memory is just terrible today, and if I run ulimit, then it'll just state what it is. If it's unlimited, you'll get core dumps. So if we run vuln, but we're going to use Python to do the print command here. I'm going to do some A's. Since it's 264 bytes, we can assume that maybe 300 will crash it and give us that buffer overrun or overflow. So we're going to give that a quick go here, and it did. So we got expected here a core dump. So we're going to gdb core to specify the file core, which it just dumped out. And as you can see, it terminated with a segmentation fault, but we see our A is in RVP, but not in RSP. So let's examine 20 hex at stack here, minus maybe about 300. We'll just start here. We're going to make note of a few things here. So we want to figure out the size first. So we take a look at the stack pointer and we say, okay, so the stack pointer is there when it terminated. What about where it begins? And that's where our 4 ones are, which is A in hex, if you didn't know. So we're going to do minus 300 here, and now we should see the beginning, but I want that to line up. And 12. So here we go. Here's the address of the beginning of our A's. So what we're going to do now is we need to do a little math and figure out how big this buffer we're dealing with is. So in order to do that, we're going to grab some help from this program called BC, which is basically a command line calculator. So we're going to echo ibase is equal to 16, and then echo, and then our values. And we want the 0x out of there because we don't need it. And then we're going to pipe that into tr, and that's going to change lowercase to uppercase. And then we're going to close our statement there, and just checking to see if this looks all right before we pipe it in to BC. And we get 264. Now if you wanted that in hex, you have to specify the output base is equal to 16. And that gives us 108, which is expected. So we know we're dealing with a buffer that's 264. So we're going to write that down. So we know we got a vulnerable buffer. Now we need to figure out, okay, so we need to get control over our IP, so which is an instruction pointer. So we're going to go gdb vuln, and we're going to do run Python tag C, and we're going to print our A's here times 264 this time, and then we're going to add some B's because, and we're going to do 6 of those just to see if we can overwrite that instruction pointer, and then we're going to close that off and give that a go, and we did. So with just a little bit of math, it works out fine. So I'm just going to copy down our Python command here. That gave us control over our IP, right? Yeah, so what we're going to do now so if we examine our IP, then you can see there that there's our B's, of course. We're going to quit this for a second, and we're going to sort of examine what we need to do to spawn a shell. So we're going to spawn shell.c. To do this, we're going to use execve, which tells us it's inside this particular header file, which is unistd.h. It takes an argument for a file name, a pointer to the what contains the string and its null terminator, and then we're just going to use envp as null. So I'm going to do into main, nothing too fancy, char pointer to something called args, which is arguments we're going to shove in there, so we're calling it that. Args 0 to going to be equal to /bin/sh, and args1, which is equal to our null byte. So we're going to do /x00, just like that. And you can specify it like this, but for today we're going to show it like that because we're dealing with binary, and it just helps us along. execv args 0, which is our first argument, which is a pointer to the string, the file, then our what contains the string and the null terminator, and then obviously null at the end here for the last argument. And then we're not going to return because we want to continue execution. Now let's compile it, see if I made any mistakes. I did, so I forgot 2, obviously. Okay, and now we got a shell, right? So let's take a look and see how we can find a system call for execv. So let's do gdb sp spawn shell and break main set disassembly flavor is Intel, then run, and here we can see we got a call to execve here. Let's take a look at that. So we can do that by doing catch sys call execve. Set a and that it tells us what it is there, but this should be a good example anyway. So we're just going to run continue, actually continues up to that point, and we're going to examine 20 hex at PC, which is where we are currently, and we notice we're inside the sub-process here, subroutine for execve. So we're going to go ahead and go back a little bit because it's a little bit deceiving. 20 I want instructions actually. So there we go. We got 3b, which in hex, well, and that's before I called interrupt, which in hex, which in decimal is 59. Where you can get that information is in here. And if we go look for execv, there it is, system call 59 or 3b in hex. So now we need to create some shellcode, obviously, to go in there to sort of try to take advantage of this. So what I'm going to do is create an ASM file here, section.txt, which is where our code is stored, and _start. That should get us an entry point. So we're going to move a keyword, which is 8 bytes, into our bx, which is going to be bin/sh, and I'll explain why here in a second. I'm going to shift right rbx 8 bits. I'll go over this once it's written out. Push rbx onto the stack, move RDI, RSP into RDI, and push array x onto the stack, push RDI onto the stack finally, move RSP into RSI, and then move array x to x3b, and syscall, which is the interrupt for 64-bit. The one for 32 explicitly would be in tox80, but in a sort of dual operating system like we have here, x86, 64, it's syscall. So what this does is it moves this into RBX, and when we shift it right, it's actually going to get rid of this little slash here and put a null terminating on the end. It seems like you're shifting it left in that case, but when we're talking about memory, it's backwards. Then we're going to push it onto the stack, and then we're going to take the stack pointer and move it into RDI just to set ourselves up. We're going to push RAX, which is our null, and then RDI, which is a pointer to our null and our string and our null, and then we're obviously going to point to the string, which we do here by moving RSP into RSI. Then we take the system call number, which is 3B, which is 59, move into RAX. We can use RAX again because it's already been pushed onto the stack, and then call the system interrupt. So we're going to now NASM tac f-elf 64, and we're going to do shellcode.asm. That's going to give us our object file, j.intel. Now we're just going to get the machine language or machine code from it. So tacd shellcode.o, and you can see, but we have a problem. We have some null bytes here, so we're going to have to go back because we can't have null bytes in a buffer, or it's just going to terminate and our code's not going to execute. So we're going to go nano shellcode.asm, and we just change this to AL. It's a smaller register than EAX. When it created the object file, it took it down to EAX automatically, which is kind of probably an optimization that NASM puts in there, but you can optimize it even further by doing AL. It's a smaller register, which basically means we get rid of those null bytes. There's, it's the pain of security because that's our backwards compatibility back when 8080 processors, things like that were around. No one wants to get rid of it. So now we're going to do this again. NASM tac f-elf 64 shellcode.asm. Then we're going to do our obj dump again, and you can see that those null bytes have disappeared. Now, now I wrote a little program here to do get these codes so into a nice string so we can use them. So we're going to do shellcode.o, and here we go. So your ticket to the pwn zone is my idea of being funny. So we're just going to punch that in here. I'm going to make this a little bit wider so I can see. So, and like this 27. So by now we should have all the things we really need to take advantage of the stack. So the beginning of our shellcode was here, if you remember correctly, if I remember correctly. If not, we'll fix it. So we're we're going to go GDB. Let's just make sure our shellcode works. So let's ld shellcode.o shellcode, and it does. It spawns a shell. So we're going to go GDB vuln run, and this time I'm going to take Python and our entire shellcode here, which is 27, and we're going to put that in here. Now we need to take away 27 from our A sled because we have to compensate because we want to land in the right place for the instruction pointer. So to 64, it's simple. Minus 27 is 237, right? 237. Now I can just replace this here B thing here with our beginning of our shellcode. So just punch that in, and we need to add the right formatting here. Don't mind me messing it up here. There we go. And if you didn't know already, that needs to be reversed. And we can do that in Python just by adding that. Because we're dealing with memory and it needs to be in little, because we're dealing with little endian format. So we should be good to go here. We're going to run Python. Here's our shellcode. We compensated for the length of the A sled, and then we're going to tell it to go to the beginning of where that shellcode is when we first did that, and we have that in our notes there. And then we're going to reverse it, just that section there, and send it on through. So let's examine here where we're going wrong. So let's go back and do our B times 6. And it does, but we need to find our shellcode. So perhaps I put the wrong one in there. So examine slash 20x. RSP minus 300. So let's just get that again. A times 27 plus that plus that. Okay. So slash 20x RSP minus 300 and 304. There we go. Here's our correct start of our code. So if we go back to here, we want to replace what I had previously. You know what I did? I had it in the wrong place. My quotation. That's why. And then we reverse it. And we get a shell. Okay, so you can see how it gets a little tricky here and there, but you can sort of work your way through it. So we're just going to exit, and I'm just going to show you this here string, and then we're going to go over that. So what we got here is we got our shell code, right, that we've created, plus our sled of A's, and then we have the values that we want to overwrite the instruction pointer. Remember, they were all B's, which is 42 in hex, but we reverse them into, because we're dealing with little endian format. So basically what happens is the instruction pointer gets this address, it fires back all the way to the beginning of where we have this shellcode here in memory, that it executes those instructions. And that's why we are able to get a shell with that method. So I hope that makes sense, and I hope you find this useful. Yeah, other than that, have a great day.